So, hello, ladies and gentlemen. I'm Edis Junaki, fluid properties expert at Tufts UK National Engineering Laboratory for over the past 2 years. Before joining NEL, as Lynn said, I was a PhD postgraduate researcher at the Institute of Geoenergy Engineering at Heriot-Watt University in Edinburgh. And now today, I would like to invite you all to have a scientific journey together through this presentation in order to explore that how CCS and hydrogen systems work and what some of the main challenges are in this way. At the end of this scientific journey, we will figure out that how chemical thermodynamics could address those barriers. Okay, as you know, human activities have increased the concentration of CO2 in the atmosphere to be much higher than what has been determined as a safe level. That's why CCS has been introduced to the world to capture CO2 and transport and store it to somewhere safe. In order to find the best place for CO2 storage, scientists and researchers got inspired from nature, in which natural gases were trapped in geological reservoirs for a million years, which then were produced and transported to the refineries, for example. That's why this conclusion was made that the oil and gas infrastructure, such as subsurface reservoirs and transportation pipelines, which have the appropriate capacities and capabilities, can be reused and repurposed for the CCS processes. However, there are some significant challenges associated with this strategy. And in this presentation today, I'd like to discuss these challenges and potential solutions in 4 steps. First, I would like to describe how a CCS and hydrogen systems are like. So how the CO2 and hydrogen-rich streams are transported and stored in geological formations after being captured from power plants or blue hydrogen production units, for example, and what the challenges are in this way. Then I would describe the problems, which parts of the system might face significant issues such as flow measurement errors, corrosion, sweet scaling, associated flow assurance challenges, and rock dissolution problems. Then I'll go through the theory and thermodynamics and try to tell you why these challenges are happening. And once we have that theoretical understanding, we will try to provide some solutions for them. Actually, assuming that the gas engineers are medical practitioners. So first I would describe the patient, who is sick, who is the patient, how is biological system like, then what is his illness, which part of his body is not functioning appropriately, then what is the main cause of his sickness? Is there any coronavirus or any unfunctionality within the body? And at the end, once we realize the reason for his illness, we will prescribe some remedies to tackle that. Okay, almost all of you might have heard about energy integration strategies to touch net zero target by 2050. One of the strategies is reusing and repurposing oil and gas infrastructure, as I said in the previous slides, for carbon capture and storage purposes. However, there are some significant challenges against this kind of CCS process. The first and one of the most important problems is inaccurate CO2 flow measurement. As you know, we need to know how much CO2 we captured from power plants or blue hydrogen production units and how much CO2 we are going to store into the geological formations. But when we capture CO2, some impurities such as hydrogen, methane, and some other components accompanied it, which makes significant errors in the performance of flow meters for accurate measurement of CO2. Those impurities can also cause 2 other problems of significant problems of corrosion in pipelines and also reservoir rock dissolution and associated CO2 leakage into the seafloor, ocean, drinkable water aquifers, and atmosphere and environment in general, as you see here in this picture. The interesting point is that all these challenges are somehow related to the fluid properties of CO2-rich streams. So if we could develop a new tool, a new reliable thermodynamic tool and model to accurately predict the thermodynamic properties of CO2 streams, we will win the game and we can somehow overcome all these challenges. So in this presentation, we will see that how we can do that actually for each specific challenge I presented here. Okay, let's dig into the first problem, CCS flow measurement. In this part of the presentation, we are going to find an appropriate answer to this significant question, that how can we reduce the errors in CCS flow measurement? In order to answer that important question, first, we need to be aware of the importance of thermodynamic properties of CCS streams in flow measurement. Here you can see the locations of flow meters in a CCS processing chain at which precise flow measurement is needed for the purposes of the custody transfer and or regulatory metering as defined in the EU legislative requirements on CCS. You can also see the range of stream composition or CO2 content, pressure and temperature ranges mainly from 20 to 80 centigrade, which are presumably to be encountered at the metering points along this CCS value chain. This information can be employed to construct a phase diagram using reliable models of vapor-liquid equilibrium and also for determination of fluid properties of CO2-rich streams. And as you know, there are some innovative technologies for flow measurement of CO2 streams, such as ultrasonic flow meter and Coriolis meter. However, there are some challenges associated with these flow meters, with using them for CO2. The most important one is the presence of a second phase, which would lead to errors in performance of these flow meters. And on the other hand, we need to accurately determine two thermophysical properties of density and speed of sound for CO2 streams to make sure about the outputs and secondary measurement of these flow meters, which is speed of sound for ultrasonic flow meter and also density for Coriolis meter, to make sure that the outputs are accurate enough for flow meter verification and flow meter diagnostics, or even for the traceability and calibration of these flow meters. So that's why we need to accurately determine these two thermodynamic properties of CCS mixtures. Okay, in this regard here, you can see the experimental data and modeling results of density values for CO2-rich systems in presence of 4 mole percent of the most common impurities, including nitrogen, hydrogen, methane, and carbon monoxide for different pressures and at constant typical temperature of 40 centigrade. We have used 5 different equations of a state, which are SRK, Payne-Robinson, Valderrama, Patel-Teja, VPT, PC-SAF, and Garrick equation of a state for our thermodynamic modeling study here in this project. As can be seen with increasing pressure, we have increase in densities of the CO2-rich streams, and compared to the pure CO2 system, the presence of impurities reduces the density of the system. The order of the density values for different systems is that the density of CO2 and nitrogen system has the highest value compared to the other gases, followed by carbon monoxide, methane, and hydrogen. And this is actually obvious since the nitrogen has the highest density compared to the other gases, again followed by carbon monoxide, methane, and hydrogen. The good news is that all the models or equations of a state could successfully predict all the trend of densities for different CO2-rich streams studied here in this slide. Okay, for ultrasonic flow meter, here you can see the experimental and modeling data of speed of sound for CO2-rich binary mixtures in presence of 4 mole percent of nitrogen, hydrogen, methane, and carbon monoxide, again, for different pressures at constant temperature of 40 centigrade, actually as the same condition for the density results I have presented in the last slide. Again, we have employed 5 different equations of a state, which were explained in the previous slide as our thermodynamic models. And as can be seen, with increasing pressure, again, we have increasing speed of sounds for CO2-rich streams, and compared to the pure CO2 system, the presence of methane and carbon monoxide impurities actually reduce the speed of sound of the system due to the larger size of these molecules compared to the CO2 molecule. On the other hand, because of the smaller size of nitrogen and hydrogen molecules compared to the CO2, the speed of sounds for those two streams are higher compared to the pure CO2 system. So the order of speed of sound values for different systems is that the system including nitrogen has the highest value compared to the other gases, followed by hydrogen, pure CO2, methane, and carbon monoxide containing mixture. The other good news here is that, again, all the equations of a state and models could successfully predict all the trend of speed of sound values for the studied CO2-rich streams here for assessment of the speed of sound experimental data and also modeling outputs we had here. Now you might have an important question in your mind, that how can we make sure about the accuracy of the modeling results if you have this question in your mind. So that's fantastic. Here you can see the model validation through comparing the experimental data with the modeling results. And here we presented actually the average deviation of the modeling results from the experimental data actually for both density and speed of sound properties to examine the outcomes of different employed equations of a state. And as can be seen, Gerg equation of a state has the lowest deviation compared to the other models employed here. So it can be safely inferred that the Gerg equation of a state is the most accurate model for determination of thermodynamic properties of CO2-rich streams as we had here for this study. In this slide, you can see the phase transition from a two-phase blend to a supercritical fluid. In the top left picture, you can see liquid and gas exist in equilibrium. A liquid vapor rounder is very recognized at this point, however, becomes progressively less recognized as the blend makes the transition to a single supercritical fluid. As the temperature is increased, the difference between the gas and liquid densities reduced, as can be seen actually in the bottom right picture in this slide. And now you can see the vapor-liquid equilibrium graphs or phase diagrams or phase envelopes of CO2-rich streams in presence of nitrogen, methane, carbon monoxide, and hydrogen impurities using the Gerg equation of a state as the best model among the others, as I presented in the previous slide. As can be seen, all these impurities open up two-phase liquid gas region, actually the problematic two-phase liquid gas region, and presence of higher concentration of impurities would shift the phase boundaries to the left-hand side. And the bad news is that actually the presence of trace amount of impurities or very low concentration of impurities, two-phase regions cover wider range of temperatures, as you see as the red curves here in these diagrams here in this slide. And this is really problematic, particularly for the operators who are operating within the offshore environment, in subsea environment, where they would face significant change in temperature along the transportation pipelines. So to wrap up, if we want to have lower uncertainties in flow measurement for CO2, we need to operate within the single phase region. So first, we need to recognize the problematic two-phase liquid gas regions and try to avoid to operate within those regions and try to operate within the single phase region to have much more reliable and accurate flow measurement outputs and results. So this is the conclusion from this. And okay, we are going to dig into the second and third significant problems, which are CO2-induced pipeline corrosion and reservoir rock dissolution. As you can see here in this slide, there is always a big concern for policymakers, government, stakeholders, and operators, and that's the risk of CO2 leakage from transportation pipelines or subsurface reservoirs into the environment. And if that CO2 leakage happens, all the efforts we have done for capturing and storing CO2 would be wasted, which is a big disaster, actually. Now, the significant question is that how can we prevent significant corrosion and leakage problems to be happened in a CCS process if we would employ repurpose actually the oil and gas infrastructure. In order to answer that question, firstly, we need to know what are the main drivers of corrosion and rock dissolution challenges. That is pH, obviously. So here you can see the anode and cathode reactions participating in electrochemical corrosions in transportation pipelines. Then we have even a trace amount of water and or hydrogen sulfide as impurity in the CO2 rich streams, carbonic acid will be produced. So we will have acidic environment, and that acidic solution is more reactive than the pure CO2 stream without any problematic impurities, and that can attack the pipeline surface and which lead to the corrosion. Due to the formation of carbonic acid, more ions like proton and bicarbonate will be released into the aqueous phase, into the brine, which increases the conductivity of the solution, and therefore the pipelines will be prone to the higher degree of the corrosion. Actually, in the case of the geological postmedia like deep saline aquifers, when we introduce CO2 into the brine, when we inject CO2 down there into the aquifers, again, the carbonic acid will be produced, and it speeds up the rock dissolution, and as a result, the CO2 can penetrate to the upper layer, which increase the risk of CO2 leakage, or in other words, the safety and security of the whole CCS process, and also geological storage site and that reservoirs will be reduced accordingly. Okay, here you can see the experimental and thermodynamic modeling results of pH changes for different CO2 brine systems in presence of different salinities for the aqueous phase. As can be seen, when we increase the salinity of the aqueous phase, the ion activity coefficient of the proton will be increased after CO2 injection process, and the pH of the system would be decreased accordingly. And this is actually means that we have more acidic environment, and the risk of reservoir rock dissolution and corrosion associated CO2 leakage would be increased as well. The good news is that, again, our thermodynamic model could successfully estimate all the behaviors of pH variations of the aqueous phase after introducing CO2 into the system, and we can safely say that our thermodynamic model tell us that the deep, low salinity aquifers would be much better candidates as geological storage sites for CO2 storage purposes. So when we have lower salinity in the aquifers, so we would have higher pH, so less acidic environment, and the degree of rock dissolution in the reservoir would be reduced accordingly. Okay, in order to validate our claim, here you can see the visual observation of the effect of salinity and pH changes on the reservoir rock dissolution and induced CO2 leakage using macro CT scanner and 3D images and video. You see two images that were taken from a rock sample on the left before the experiment and on the right after the experiment exposing to the CO2 saturated brine. The light gray color is related to the grains of the rock, and the black color is for pore spaces. In this video, you can clearly see the red color, which highlights the dissolved grains. So these regions are illustrated as pore space in the image on the right. And these 3D images enable us to calculate the volume of dissolved grains for different conditions, for testing conditions. So based on the results, the pore space for the rock sample, which was exposed to the high salinity brine with lower pH, was increased 18%, while the rock phase decreased 4%. So the rock sample in contact with the low salinity brine, we have the increase in pore space, which was measured 9%, and the reduction in the rock phase was 2%. By comparing the results here, we can conclude that the high salinity brine and lower pH environment has induced more rock dissolution, actually as discussed in the previous slide and described by our thermodynamic model. Okay, very good. So let's talk about the hydrogen systems as well. I'm going to present you the background about the small hydrogen, the importance of hydrogen. Why do we need to use hydrogen as clean fuel? Why is hydrogen flow metering important? And also, I will talk about the significance of thermophysical properties of hydrogen streams for different processes, from hydrogen production to its storage in geological formations. In order to determine the properties of hydrogen-containing mixtures, firstly, we need to know what the composition of the stream is, and also what the temperature and pressure conditions are, as we use these data as inputs of thermodynamic models. In this study, we have used an appropriate equation of a state, Gerg equation of a state, integrated with a model for prediction of hydrogen-containing systems properties. And at the end, we will see that how these predicted fluid properties could be employed for optimization and designing a secure hydrogen geological storage process and accurately measuring hydrogen stream flow rates. And this is very important for us to have accurate hydrogen flow measurement, since, for example, we want to make sure that we are getting that much amount of hydrogen we paid for at the fuel stations at the end of the day. That's why it's very important for us. to have reliable and accurate hydrogen flow measurement and also determination of thermodynamic properties of hydrogen-containing systems. Now we are going to answer this question: why do we need to study about hydrogen streams? As all of you know, in order to achieve a net zero target by 2050, we need to decrease the amount of carbon emissions from fossil fuels, and the energy transition strategies to employ lower carbon energies should be undertaken. In this regard, hydrogen has a great potential to help us with decarbonization of our environment in different sectors, including transportation, heat, and power, actually. In this regard, we need to understand about the properties of hydrogen-containing systems, but the question is that what are the compositions of the streams? As you know, around 96% of hydrogen is coming from blue hydrogen production. So we call it blue hydrogen, which is produced through a methane reforming process. For producing around 1 kilogram of hydrogen, around 7 kilograms of CO2 is also produced. So we're required to also capture and store CO2 after the methane or natural gas reformation process. So in the system, we would also have methane, natural gas, and carbon dioxide, and all these gases and species would be mixed with hydrogen at different molar fractions. So we need to include the CO2, methane, and natural gas as impurities in the hydrogen rich streams, and we need to take into account them for fluid properties determination, which they greatly affect on the physical properties of hydrogen containing systems. As I mentioned before, for each thermodynamic modeling study, in addition to knowing what the compositions are, we also need to know that what the operating conditions of interest in hydrogen-based systems are. And when we use the thermodynamic models for determination of thermodynamic properties of pure hydrogen, we have well-established data in the literature, but we have some limited data, unfortunately, in the literature regarding the properties of gas mixtures related to the geological hydrogen storage, which do not cover the full range of additional gases and often do not encompass the pressure and temperatures encountered within the hydrogen storage system. Here in this slide, you can see the pressure and temperature ranges for different hydrogen-based economy systems, including vehicle storage tank, surface storage tanks, hydrogen production technologies, transportation pipelines, and etc. Here you can see the potential applications of thermodynamic properties of hydrogen-containing systems for geological hydrogen storage, flow metering, gas separation, and other types of hydrogen storage purposes, such as gas hydrates or metal organic framework. The thermodynamic data like vapor-liquid equilibrium diagrams, viscosity, and density data for hydrogen-containing systems can enable scientists and researchers to have a deeper understanding of reactive flow-through porous media for hydrogen geological storage purposes, and it can also be employed. Those properties can also be employed actually for the accurate flow measurement of hydrogen streams. So in general, the thermophysical properties of hydrogen-containing gas mixtures over a wide range of pressures and temperatures can be used to design and optimize hydrogen production units, and also for optimization and designing the hydrogen transportation and storage processes. Okay, in this study, the established and well-regarded Gerg equation of the state was integrated with supertrap model to predict the phase behavior, density, and viscosity of gas mixtures relevant to the hydrogen transportation and storage processes covering the thermodynamic properties of gas phase, liquid phase, and supercritical regions. In the Gerg equation of a state, we have used dimensionless Helmholtz energy, which is a function of inverse reduced temperature, reduced density, and also molar composition of gas mixture, and consists of two parts. The first part is for the ideal gas contribution, as you can see here, and that is function of number of mixture components, and also a function of mole fraction of each component in the system. The second part is actually residual part of Helmholtz energy, which is again a function of dimensionless Helmholtz energy of component I in the ideal gas phase, and the departure function, which is again function of density, temperature, and also composition of the system. For determination of the viscosity of the system, we use a super trap model that is composed of a dilute gas and residual contribution part and is function of temperature and density again. Okay, very good. In this slide, you can see the predicted densities for different hydrogen mixtures with methane, carbon dioxide, and the typical North Sea natural gas for mole fraction of 90% for hydrogen over a wide range of pressures and temperatures using Gerg equation of a state. You can also see the composition of utilized North Sea natural gas in this study presented in the blue table here. And as can be seen, the density values of mixtures are greater in the presence of CO2 compared to the methane and natural gas in the studied systems, as the density of CO2 is higher than that of methane and natural gas, and for natural gas is higher than methane accordingly. The densities of the streams increase with increasing pressure based on the Boyle's law, as you know, for all isotherms, and reduce with increasing temperature, actually based on the Charles law in the chemical thermodynamics. And here you can see the estimated density values, again, for various hydrogen streams with methane, carbon dioxide, and the North Sea natural gas for mole fraction of 50% for hydrogen at various pressure and temperature conditions. In comparison to the results from the previous slide, we can clearly infer that the density values of the mixtures in presence of higher concentration of hydrogen are smaller compared to the low hydrogen concentration of the containing systems. So again, here we can see that the same trend of density changes with temperature and pressure, and the densities of the mixtures increase with increasing the pressure for all temperatures, for all isotherms, and decrease with increasing the temperature, as you can clearly see in this slide. Now we are going to present the modeling results for viscosity. Here you can see the modeled viscosity values for various hydrogen blends with methane, carbon dioxide, and natural gas for hydrogen mole fraction of 10% over a wide range of pressures and temperatures using integrated Gerg equation of a state and supertrap model. The viscosities of the mixture increase with increasing pressure and temperature, as you can see here, and this can be attributed to the fact that an increase in pressure or temperature increases the velocities of the random motion of the molecules, and as such, collisions of the gas molecules increase, which resists the flow of the gas and increases the viscosity accordingly. So the on the other hand, we can see that the unusual behavior of the methane or carbon dioxide rich blends at lower temperature is because of their proximity to the methane or carbon dioxide critical point at the studied conditions here. And here in this slide, I'm presenting you the viscosity values for different hydrogen mixtures, again, with methane, carbon dioxide, and natural gas, but this time for hydrogen mole fraction of 50% at different pressures and temperatures using integrated Gerg equation of a state and supertrap model. As compared with the results in the previous slide I presented to you, we can safely say that the viscosities of the mixtures are suppressed with increasing hydrogen mole fractions in the system, as hydrogen has a significantly lower viscosity compared to the methane, carbon dioxide, and natural gas due to its smaller molecular size, actually. So this is the reason for observing such behavior in the studied systems. Okay, so as you know, the blue hydrogen production through methane reforming is an endothermic process, and it needs a huge amount of heat to be done, actually. So on the other hand, when we inject hydrogen in depleted gas reservoirs for hydrogen storage purposes, it will be mixed with methane and potentially have a reactive flow through porous media due to the chemical interactions with rock surfaces, due to the high temperature and high pressure conditions in that environment. So it's really important for us to understand thermal conductivity and thermal capacity of hydrogen and methane blends particularly. And in this slide and next slide, I'm going to present you these properties of hydrogen methane mixtures in details. So in this slide, you can clearly see the estimated isobaric heat capacities for different hydrogen methane mixtures for various hydrogen mole fractions over a wide range of pressures and temperatures using Gerg equation of a state. Thermal capacities have higher values for higher hydrogen mole fractions, as the heat capacity of pure hydrogen is significantly higher than that of pure methane at temperatures and pressures above the critical point of the methane, actually. Generally, it can be noted that with increasing the pressure, the thermal capacities increase for all temperatures, for all isotherm and temperature conditions due to the increased intermolecular forces within the system. And the peaks in the graphs you can see here can be attributed to the fact that the near to the critical points of the components, the heat capacities undergo sudden changes because of the changes in their phase. And in these examples, you can see here, as the temperatures and pressures are close to the critical conditions of methane, peaks have emerged. So with reducing the mole fraction of methane in the composition of the systems, we would move the system away from the critical point, and as such, the peaks reduce and even do not appear, as can be seen in the graph IV at the right bottom of this slide. So this is the phenomenon behind the behind our observations. Also presented modeling data for estimated thermal capacities for binary hydrogen methane mixtures at different mole fractions of hydrogen. Here in this slide, you can see the predicted thermal conductivities for different hydrogen methane mixtures, again, with a range of hydrogen mole fractions over a wide range of pressures and temperatures using integrated Gerg equation of a state and supertrap model. Again, as I explained actually in the previous slides, it can be inferred that for all hydrogen methane mixtures, the thermal conductivity values actually increase with increasing pressure for all temperatures on isotherms. Thermal conductivities also increase with temperature for high hydrogen mole fraction systems above 50%, as can be clearly seen here in this slide. These behaviors can be attributed to the fact that increasing the pressure or temperature increases the molecular motion within the system, and as such, it would improve the conduction of heat within the gas molecules. The unusual behavior of methane-rich streams here at a lower temperature is because of the proximity of those points to the methane critical point, as mentioned before in the last slide, for the thermal capacity. And generally, thermal conductivity values increase with increasing hydrogen mole fractions, as pure hydrogen has considerably higher thermal conductivity compared to the methane, to the pure methane stream. So, and this is the reason for such observation for thermal conductivity changes for different methane mole fractions within the system. Okay, here you can see the vapor liquid phase envelopes calculated for the hydrogen natural gas, hydrogen methane, and hydrogen carbon dioxide systems studied here, as presented in this slide. As can be seen, some parts of the problematic two-phase liquid gas regions of the hydrogen CO2 and hydrogen natural gas system occur within the pressure and temperature ranges of the geological storage sites and also transportation pipelines, and also as such the systems as such we studied here in this study. So it's not good at all. As I mentioned, for the CCS systems, we need to avoid these problematic two-phase liquid gas regions to have, for example, much more accurate flow measurement results for the hydrogen-rich streams. Now, again, the big question is that how can we be sure about the accuracy of the predictions and the results presented in the previous slides? How are the Geiger equation of a state and supertrap model, for example, and their integration would be accurate? So in this slide, we try to examine this, and generally the determination of the accuracy of the Geiger equation of a state for such binary mixtures as studied here in this study actually is very challenging task, to be honest, as there is no experimental data available for some specific ranges. Therefore, the absolute value of error for such range is considered to be unknown. So here we have utilized some published, some limited data, density data of hydrogen and methane blends in the literature at a range of pressure and temperature conditions to statistically analyze and assess the reliability and accuracy of the obtained modeling data from the Geiger equation of a state. As you can see here in the graphs, II and IV present the relative deviation of the predicted densities of Geiger equation of a state from the published hydrogen methane blend experimental data, and the average absolute deviations of the Geiger equation of a state calculated data used in this study from the experimental data for different pressures and temperatures are around 0.044 for the hydrogen mole fraction of 10%. A mixture, and also it is 0.006 for the hydrogen methane mixture with hydrogen mole fraction of 50%. So the low average absolute deviation values safely confirm that the high accuracy of the Geiger equation of state predictions with relatively low errors, as can be seen here in this slide. Very good. Okay, to wrap up, we are going to summarize and highlight some key points in this study. What are the problems if we want to reuse and repurpose oil and gas infrastructure for CCS and hydrogen applications? We would face some challenges related to the, for example, errors in the flow measurements, as well as the high risk of corrosion and rock dissolution problems, which lead to CO2 and hydrogen leakage into the atmosphere. We saw that all these challenges are somehow related to the thermodynamic properties of CCS and hydrogen-containing systems. So firstly, we need to understand the theory and thermodynamics behind the whole CCS process and hydrogen value chain. And in this regard, we need to develop an appropriate model to predict the properties of CO2 and hydrogen-rich streams, such as density, speed of sound, respective phase boundaries and phase envelopes, and even pH, in order to have much more accurate flow measurement and safer and more secure CO2 and hydrogen transportation and storage processes at the end of the day, through avoiding the the operating conditions which lead to corrosion and the reservoir rock dissolution precipitation challenges, which again lead to the big disaster of CO2 or hydrogen leakage into the atmosphere and environment. And if that would be happen, to be honest, all the costs we spend actually for CCS process or the hydrogen transportation and geological storage processes would be wasted, which is not desirable at all for the operators, and we need to avoid those challenges through applying the potential solutions I have explained throughout this presentation, and hopefully we could apply some of them in not only in the lab but also in the field scale, which is very important for us. Now, I would like to greatly acknowledge our main sponsor, UK Department for Business, Energy, Industrial Strategy, and also our scientific partners, University of Edinburgh and Research Centre for Carbon Solutions at Heriot-Watt University. Regarding our forthcoming events within the next couple of months, we will have a webinar on Introduction to the Wet Gas Flow Measurement on 24th of March. And also we will present a webinar about hydrogen flow measurement to support gas grid decarbonization on 21st of April. And also we will have an online measurement focus group meeting on 26th of May. Please feel free to register and attend all these events, and hopefully you will find them interesting and useful at the end of the day. And now I would like to end up our scientific journey with this nice statement from Hydrogen View magazine regarding our hydrogen thermodynamic studies, which is new innovative software. Actually, thermodynamic software could revolutionize delivery of low carbon hydrogen. So thank you so much for your time and attention and joining me for this webinar. And I would be more than happy to answer all of your questions. Please do not hesitate to contact me and send me your questions if you have any, and I will be happy to answer them. After this, we will have the Q&A session, as you know, which will be handled by Lynn Hunter. So thanks a lot. So Lynn, the stage is yours. Thank you.
Excellent, Idris. It's an excellent presentation, like you're at the end on the innovative software, but an excellent presentation and insight into obviously the issues and challenges surrounding what is a notoriously very difficult area, i.e. physical properties or thermodynamic properties. Now, I'll start to run through the question and answers. We'll probably got 5-10 minutes. Now, these are starting to really pile up, so thank you very much for submitting these, and we'll do our best to get through them. Those that we don't get through, as Idris said, we'll contact you direct, so they won't remain unanswered. So bear with me. So Idris, you ready?
Yes.
Right, here we
sure,
go.
I'm ready.
Right. Okay. What is the difficulty in having one-phase flow in these flow meters?
If we have one phase flow, you said.
Yes.
If we would have one phase flow, the other potential difficulties with flow measurement, we probably don't have that much difficulty regarding the fluid properties. For example, the phase diagrams and also presence of two-phase liquid gas, so we don't have that problem. But we need to be careful about the. We might have some difficulties regarding liquid CO2 flow measurement, which is really challenging. For example, at NEL, we have the capabilities and facilities to measure, CO2. We have, large flow loops for CO2 flow measurement, but in the gas phase, not the liquid phase. So the difficulties could be the measurement of liquid CO2 would be, very challenging for us. So that would be the challenge if you have single phase. But for the gas phase, it would be, much easier. Yeah.
Okay. Yep, they'll answer. But just moving on to the second question I've got here. What is the uncertainty of the experimental data for density and speed of sound?
Very good question. Actually, the expanded uncertainty, the relative expanded uncertainties for these experimental data are between, if I do remember correctly, is between 0.02 to 0.05. So it's relatively low uncertainty. So the experimental data is very valuable and reliable actually for model validation and verification of the modeling results. So yeah, the uncertainty, in total is very low. Yeah.
It's pretty good. Okay, which technology and device are you using to build the porous network and to access the pore space to see the rock dissolution due to pH changes?
Yes, actually, we have employed a Macrocity scanner and a Macrocity imaging actually to monitor the reactive flow through porous media, the reactive flow of the CO2 saturated brine in porous media in presence of different salinities, and also to investigate the effect of pH changes on the reservoir rock dissolution or the rock sample dissolution actually and precipitation. So Macrocity imaging was being used to understand porous scale phenomena of CO2 saturated brine flow through the geological porous media. So the answer is Macrocity imaging technology.
Okay. Okay, now, try to reword this one. The comparison between model and experiment has only been performed for density. So what about, for example, viscosity, thermal capacity, thermal conductivity?
Yes. Actually, as you saw in the presentation slides, for the CO2 rich streams, I presented the data not only for density, but also for speed of sound. But for hydrogen, as I mentioned in the slides, Actually, we have limited data available in the literature for specific composition ranges and also for specific operating condition ranges, for example, pressure and temperature. So that's why we have difficulty to find appropriate data for for a specific range of composition, a specific range of impurities and pressure and temperature operating conditions. So that's why we have found the available data for that specific range, composition, and pressure and temperature range for density, but not for viscosity, thermal conductivity, and thermal capacity. But actually, the literature would need data for those properties as well for different mole fraction of impurities and also for a wide range of pressure and temperature conditions.
Okay. Now, was the experimental work based on new research or previous or old research which was previously published? So if you give us a bit more an insight into what were sort of sources of the experimental work.
Yeah, good question. Actually, as I mentioned, I think in my slides, we got the data, the experimental data for the density, speed of sound, and also for the density for the hydrogen system, and those two ones for CO2 rich streams. We got them from the literature, so there are the data available in the literature in different articles. But also we have the capabilities and facilities at NEL. We have high pressure, high temperature densitometers. So as you know, many of attendees might know that we are UK designated Institute for Flow and Density Measurement, and also we are UK national standard holder for density measurement. We have different densitometers and for high pressure, high temperature determination of density at elevated pressure and temperature conditions. I mean, particularly for the CCS applications. Yeah.
Okay. Now, the CO2 and carbon dioxide parameters are not correct in the original Gerg 08 equation of state. So have you corrected these for this piece of work?
Pardon, could you please ask your question again?
I'll read it a bit slower. So the CO2,
yes.
the CO2 and carbon monoxide parameters are not correct in the original Gerg 08 equation of state. So have you corrected for these in this research? Yes.
Yes. Exactly. Yes. Actually, for the you know, having much more reliable results and accurate results, modeling results, we need to tune some parameters within the equations of the state. For example, binary interaction parameters, and also we need to choose appropriate mixing rule, for example. But anyway, for this case, the binary interaction parameters between, for example, hydrogen and CO2, as mentioned in your question, should be tuned, should be optimized actually based on the experimental data, if that would be available, and that is actually what we have done for our studied systems using the Gerg equation of a state. Yeah.
Okay. Right. Next one. So with the results for density and viscosity, does it mean that it's better to create a cushion gas? A cushion gas with low H2 for better drainage, and just then inject rich H2 through the stream for storage. So I'll repeat that one, okay? Because I was
so I think that this question is regarding the cushion gas. Actually, so if you would use, for example, CO2 as a cushion gas, if that would be technically feasible, so we need to investigate this further anyway. But if we use CO2 as cushion gas in the system, we might have some. It would be really valuable for us to determine the thermophysical properties of CO2, for example, and hydrogen mixtures, since the CO2 could be mixed if the transition zone in the geological reservoir would be small and too tiny. They might be mixed, and so it would be really valuable for us to determine the thermophysical properties of them. If we would use other gases, for example, methane or natural gas as cushion gas for hydrogen storage purposes, and for producing hydrogen actually during the, for example, winter, when we want heat and energy, from hydrogen. So we need to study the thermophysical properties of those mixtures, natural gas, methane, and hydrogen as well, if we use them as cushion gas. So I think that would be the answer for this.
Okay. Now, what are the limitations on your NEL thermodynamic package, and are there any commercial names available for the package as yet?
Yes, we have some limitations in our thermodynamic package, like PPDS, for example, for, when we want to involve salts in the system, we need to, optimize the binary interaction parameters between each salts, each component, each ions in the system with the gas components. That would be really, valuable for solubility determination, for example. So we have a bit limitation for including, for example, ionic components within the system. For example, if we want to investigate the effect of some salts in the system, some specific salts in the system, it's better to say. So we have, some small problems with it, but we need to improve that. So I think that compared to the other commercial software, I think that we need to improve this in this way. Yeah.
Okay. Right. How do we determine the uncertainty and density, standard density, speed of sound measurements to allow us to complete uncertainty calculations for metering systems, which is something I was thinking about during it as well. So just I'll repeat it. How do we determine the uncertainty and density, standard density, speed of sound measurements to allow us to complete uncertainty calculations for metering?
Actually, we have, different, for example, when we, calibrate our densitometers using the calibration fluid, we have we have a specific uncertainties to pass the densitometer to say that, okay, the densitometers are well calibrated, for example, for that specific fluid, and that would be something lower than 0.02 or 0.002 or 0.003, so something like that at highest degree, at highest level. I think it's 0.03. So we include that in the metering outcomes when we want to convert the volumetric flow rate to mass flow rate or vice versa. We need to make sure that, okay, our density values for that specific system for that particular fluid is within that uncertainty range, as I mentioned, and that would be really important to have more accurate flow measurement results at the end of the day. Yeah. And
okay,
actually, for the secondary measurement of Coriolis meter, which is the innovative flow metering technology, is density, as you know, and having reliable density values with low uncertainties, both in the lab and also from the modeling data, would be very valuable for flow meter for Coriolis verification and diagnostics, and that would be very useful in this regard. Yeah.
Okay. Now, on that basis, following on from that, why only ultrasonic and Coriolis? What about other types of meters like Venturi, Vortex, Orifice, Multiphase? Have you got a quick answer for that? Because I'm going to start rounding up. We've got a lot to get through.
Yes, exactly. Yes, they could be also considered as the appropriate metering technologies, like Venturi tube, for example, or DP flow meters. But what I have mentioned here, I mean, ultrasonic flow meter and Coriolis meter, because the secondary measurement of these flow meters are fluid properties, actually, speed of sound and density. So we could employ them, the accurate thermodynamic modeling outputs for flow meter diagnostic or even for calibration of them. And also the speed of sound for ultrasonic flow meter could be employed for compositional monitoring of the CO2 rich streams, for example, since the speed of sound is function of composition of the system. So based on the speed of sound determination, we can monitor, we have online monitoring, we could have online monitoring of the gas composition changes in the CO2 stream, which is very valuable for the operators. So that's why these two flow meters, which are, very close to the fluid properties and thermodynamic, I mentioned them here in this presentation. But obviously, we could employ the other metering technologies for CCS. Yeah.
Right. Now, there's lots and lots of more questions, so I'm going to start to round up, and we'll obviously answer the remaining ones. Very, very pleased, obviously, with the amount of interaction, and appreciate the amount of questions that have come forward. They really do make these sort of events more engaging, etc. And I think as some of the questions touch upon is things like collaboration, and you can see why this is necessary. So again, thank you, Idris, for the talk. Now, and again, thank you to all the delegates, etc., and participants who came forward with questions. I'd just like to say, please feel free to contact myself or Edris after the event, just to understand a bit more about what we're doing, what you're doing, and to look up potential collaboration. I think it's worth pointing out, as a government-funded body for metrology flow measurement, we have a duty to disseminate through a knowledge transfer programme our different bits of work in this area. And yes, it's very much needed, I think, greater collaboration. So it's good I use government money and to ensure it's been spent in the right areas. And it's no secret that collaboration always sort of yields much greater results, greater impact. So we would certainly encourage yourselves to sort of get in touch, and also feel free, obviously when times are better after COVID a bit, to come and visit our facilities in East Kilbride. So as we said earlier, everyone will get a copy of the presentation. You get a copy, obviously any questions will be answered as well, and hopefully we'll get to hear from you at a later stage. So I think it's all that's left to say now, just obviously goodbye from myself, Edris, and the webinar team at NEL, and obviously stay safe and enjoy the rest of your evening. But thank you very much for taking time out today to join us.
Yeah, thank you so much for your time and your attention. Thank you. Cheers.
Thanks,
Bye.
Thanks. Bye.
Bye.